Darn it. It's recording now.
Well, I got a quick question for you. It has
Yes.
to do with the equation solving for M2.
The one that we used up here?
Yeah.
Okay.
So I was following with it, writing stuff down and trying to plug things into my calculator as well. And I've tried plugging that part of it in twice now. And both times I get 56,671,741.
Did you make sure to multiply this? The big G and this is just, that was a little bit of a messy pen on my part. That's negative 11, right? But then when you multiply this, but don't forget,
that could have something to do with that.
If it was negative 17, don't forget too
Yeah,
that
that's what I wrote.
these are both on the denominator. So when I do it in my calculator, I usually divide by one and then divide by the other. But if you want to multiply them, that's fine as long as there are parentheses around the two of them together.
Yeah,
But if you read that as a 17,
and I just use parentheses.
if you use that as a 17, then that would make a difference of about
6 decimal places?
a million.
That's what it
a million
was.
different. So that would make it, yep.
I fixed it. Now I got the same number as you.
Hooray.
So.
Well, and this right here, putting that 5 in there is a reason that if I notice that's the error on a test or something, I'm not that harsh about it, because I've done hundreds or thousands of these and it still gets me every once in a while. Okay, other things you'd like to talk about?
Could you work through problem 8 on the baseball?
Mm-hmm. So it says Mars is 10.7% the mass of Earth and has a radius of 53.3% of Earth's. What is the gravitational acceleration on Mars? So this is another good one that makes use of, maybe we don't have to calculate every single step, but we can use some comparisons that are really, really close. So we know that, just like I had up above, there were two ways that we could write this. Force of gravity, mass times the acceleration of gravity gives us a force. But then also, always, our main big formula here. And it is important to note that one of these two masses, either 1 or 2, is the mass of the planet that you're on. The other is the mass of the object that you're measuring. And so I'm just going to call this M1 in the first place, just to make sure we keep that in mind. M2 will be the planet mass. Okay, so the question is, what's the gravitational acceleration on Mars? And we have some comparisons to what it is on Earth. If we just look at the right hand, this portion of these, we have a relationship that can help us find what the acceleration of gravity is on different places on Earth or wherever. We notice that M1 appears on both sides of that equation, so we could divide through by it and just say that the lowercase g, the acceleration of gravity, must be equal to big G times M2, the mass of the planet, divided by r squared, which is the radius of the planet squared. And of course, we know what that's going to work out to on Earth. It's going to be 9.8. We don't necessarily know what it is on Mars. We could look up what the size of Mars is and its mass, but it does give us hints comparing it to Earth, and Earth we've already used before even today. So I'm going to use those comparisons to Earth to figure out G on Mars. So I'm going to say G on Mars here. We know that the big G is always 6.673 times 10 to the negative 11 newtons times kilograms squared over, times meters squared over kilograms squared. Now the mass isn't given directly, but we do know that it is 10.7% the mass of Earth, And remember what the mass of Earth is. I just used it up above. It's 5.97 times 10 to the 24 kilograms. But Mars is only 10%, 0.7% of that. So I'm going to multiply that number by 0.107. Now I have the mass of Mars.
Are we just supposed to like know that it's like 10% of Earth's gravity, or like how would we figure that out?
If you read the question, it says Mars is 10.7% the
Okay.
mass of Earth.
I didn't have the question, so I was like,
Yep. No,
how
I
did we
figured
just
that was
figure
the
that out?
case. Yep. I would not expect you to know that. And on the test, I have the mass of Earth already there. So if there
Okay,
were some
perfect.
comparison, you could use that. And then, okay, so then radius squared, we know that it's 53.3% of Earth's also over there. And the radius of Earth was you can see at the top of my screen, 6.378 times 10 to the 6th meters. But I have to square that whole thing. Okay, and now multiplying these together should give me gravitational pull on Mars. I'm just going to scroll down for this one. Yep. So it comes out to be 3.7. How many sig figs? Should have done it with one more sig. 3.77 meters per second squared.
What is the difference between the force of gravity and then the gravitational acceleration?
The force of gravity is the full force in newtons. So if you wanted to find out what your weight would be on Mars, we wouldn't have factored out the m1 from that equation. We would have just figured out the whole thing. And we could have used the same numbers for the mass of Mars and the radius, but we would have kept m1 in there. Force of gravity is your weight. The acceleration of gravity, as we remember from first semester, we used to find it just m times g, the mass of the object times the acceleration of gravity, but now we're branching out a little. So it might not just be the acceleration on Earth, it could be somewhere else, like in Mars. And I'm not sure why I actually took an extra step. I'm looking at more carefully at my solution and then multiplied. That doesn't make any sense what I did there. So skip that last step. I'll correct that in my solutions. This is actually our appropriate answer, and I can figure that out carefully if I look at my units. So I've got meters squared on the bottom, meters squared on top. I've got a kilogram here and a kilogram here, but that only takes care of one of them. So I end up with this as 3.77 newtons per kilogram, which is meters per second squared. So I took an extra step that was not appropriate in the solutions, and I'll fix that soon. We probably got time for one more question today with the group.
I have just a really quick kind of random question just because I'm blanking. What's the big G stand for again?
Big G is the universal gravitational constant, something
That's
that
just a solid number.
it's just a solid number, always with the value that I've been writing it with here. And it applies throughout the universe in any normal conditions. That's something that comes from Newton's work, and we've refined it since then. But
Mr. Sklenica, so I was looking at like your doubles, and basically for both of them, you kind of like use the logic that the centripetal force equals like the gravity on a planet. So, but is that like, I don't know, is that all the time? Like, can you, I don't know, just explain that?
So first question is, what is Earth's average linear speed in its orbit around the sun? There are a couple different ways you could do that. If you know the distance from the average distance from the sun to the Earth, you could figure it out just by taking the radial distance or circumference around, dividing it by however many seconds are in 1 year, and you get pretty close. So that is a way you could do it, but we already know a couple other things about Earth's movement. Are you dancing to no music or dancing to some music? And there are two ways we can express the force that Earth is feeling. We could do it gravitationally, which would be big G times the mass of the Earth times the mass of the sun divided by the orbital distance of the Earth to the sun, the average, so whatever one astronomical unit is. But it's also going almost in a circle. So if we take that as an average, it's really, really close to a circle. And if something moves in a circle, we know that it's got centripetal force, which would be equal to the mass of the object, in this case, Earth, times its square of its velocity, divided by the radius of its movement. These two things are both describing the force that's keeping Earth going in a circle, so they must be equal to one another.
Okay, so like the gravitational force here and the centripetal force, you can only like set them equal to each other when the orbit is like basically a circle?
Yeah, and
Okay.
that will be most of the things that we are looking at are really close to circles. Most of the planets are quite circular, not strongly elliptical. So that would be
Okay.
pretty fair to do most of the time. Second one, International Space Station is 108.5 meters long. If it were set to spin about its center, what period of revolution would result in a normal gravity feeling while standing on its outside walls?
Yeah,
So
and
that
that's
one,
just the circle too.
yeah, that one's a circle too. This one, we know that if it's spinning, it's going to have centripetal motion over r, and we want to create the feeling. So this is the feeling that something with a mass m would experience being on the outside spinning around. We want that to be like Earth. Well, we know that Earth's gravity is expressed as m times g. These two now have to be the equal parts. And that's what makes these two questions doubles rather than singles. The actual calculation isn't very hard, but the recognition that those two things are describing the same force is the tough part. So having those two equal means that while the m's are the same, this is a mass that is either here on Earth experiencing normal gravitational acceleration, or on the one end of the space station being spun around. So the m part cancels, and v squared over r must equal g for this to be true. And we wanted the period of revolution. So that relates to what is v? Well, v is the distance traveled by the period of the revolution. So how long does it take to go around in a circle? The distance traveled would be 2 times pi times the radius of whatever the circle it's moving in is, divided by t. So I'm going to put that into for our v squared up here, and we get 2 pi r over t squared, and we're still dividing that by r is equal to g. Or simplifying that a little bit, 4 pi squared times r squared, and then on the bottom we're going to have a t times an r. And of course that r on the bottom cancels with one of these. And then we wanted to solve for t, so I'd multiply both sides by t, divide it by g, and we'd get that relationship, which we could then put some numbers in and find it.
Would the t be squared?
Thank you. I was just looking at that, t squared, so then we'd square root both sides. T then would be, we could simplify this a little by taking 2 pi, but then we'd still have R over G and under the radical. Always let units help you with that, because of course there's no units on 2 and pi. The unit on the radius would be meters. On G is meters per second squared. So the meter parts cancel. And this would be 1 over second squared, which would give us in total second squared under the radical. Taking the square root would lead us to seconds. And that would make sense then for the period of revolution. Yeah, so this is a tougher one, not simply because of the math, but really those relationships. And so to the previous point, on double number 1, if you're looking at a force ever, if we're moving in circles a lot in this chapter. So it's entirely possible that both of those formulas, both gravity and centripetal force, both describe what we're talking about. And it is the end of our time together. So if anyone wants to hang out and has an extra question, you are welcome to please ask. Otherwise, like I say, I am available just for pop-ins at 10 tomorrow, but if you have a question, you can always email me and we'll either set something up or answer it over email.
Are there any questions on the test that aren't covered over the baseball questions?
There are
That we
always
should
some that
look
are
into?
more conceptual in nature.
Okay.
Let me bring that up and just see, without giving you a direct, yes, do this. I can guide that a little bit. Yeah, we didn't. So the conceptual questions, we did talk a bit about seasons. You had a reading about tides. Make sure to not neglect those as you were going back over. We could definitely have a discussion about both of those tomorrow. Yeah, that's the main thing. The conceptual questions, the calculations are all really closely related to things that we're practicing with the baseball questions. So in that regard, it's a good review. And then don't forget to review the conceptual parts of this chapter as well.
Well, so
Okay.
so we do need to know about tides and seasons.
Yeah, we should. Well, for this test, yeah, and so we should chat about that tomorrow.
Okay.
We did talk about enough about seasons yesterday, which makes me sad for Tessa and whoever else missed and I forgot to record. But we can definitely chat more about that.
No, I was confused because yesterday you said we didn't when I asked. You
Yep.
said we didn't. And
Yep,
then...
I remember. We got time. This is a big adjustment for all of us. We won't be doing we don't need to do the lab. That part stands, but I'd forgotten that question was on the test.
So we will go over them tomorrow.
We sure
then?
can. Yep.
Okay.
So review and see if if you have any questions, and please bring it up. And help me remember to record. Even if you ask, hey, are you recording?
Will do.
Anything else before you sign out? Don't forget, so we've got, I don't know if you've heard, there's this illness going around. If any of you become sick, like really sick, and don't like stress out and kill yourself trying to do everything for class, we can be flexible. So make sure to take care of yourselves first. But just let me know so that we can plan accordingly. But the whole point of this is that we're being flexible. So if that means you have to take 2 weeks until you feel well enough to do it, that's something we can accommodate. Okay. Well then, I will talk with you tomorrow.